Let us go through another data structure which is called as queue. Now we have seen simple arrays, then stack, multi-stack. Now it is a queue. The queue representation will be like this as shown in the figure. Insertion and deletion are the two operations, main operations. Insertion is done at one end and deletion is or removal is done at the other end. So whatever value goes into the structure will be taken out first. Therefore, a queue is called as first in, first out data structure or FIFO data structure. So the insertion and deletion of the elements into this structure will be happening at two ends. When we enqueue a value, that is push a value, if we are considering it with a or comparing it with a stack, pushing a value is called as enqueuing and popping a value is known as dequeuing. If we push a value, that end is called as rear end and the removal end is called as the front end. So as in the case of stack, we were using top as the point of operation. Here we have two operations at two ends. So the pointers have to be two in number. They are rear and front. Rear and front are the two pointers used along with this data structure queue. It is called as first in, first out data structure. Let's see some terminology associated with a queue. It is a linear data structure. Linear means there will be elements one after the other. It is called as linear data structure. If X is an element, it may have another element Y after this X. And there will be only one element after X. Such a structure is called as linear data structure. Q belongs to such data structure. I have told you it's a FIFO structure, that is first in, first out. Operations will be performed in this manner. Whichever value gets into the structure first will be taken out first. The elements added first is removed first. That is the meaning of FIFO. Element added to the list first is removed first. If there are two elements, whichever added first is removed before the second one. And the addition is done through one end, which is called as the rear end, and the removal is done from the other end, which is called as the front end. The technical name for adding operation is enqueuing and that of removing operation is dequeuing. So these are the main terminologies used along with the data structure queue. Let us see a labeled diagram of a queue. As we have done with the stack, we have to define an array with a maximum capacity to hold some values. That will be the limiting factor of that queue. Here in this example, there are 4 elements. So the size of the queue or size of the array is 4 in number. And this end is called as front. We can take either this end or this end as the front end. The other end opposite to that front end will be considered as the rear end. The dequeuing operation will be performed from the front end and the enqueuing operation will be performed from the rear end. As I have told you, we will be using 2 pointers. They are front pointer and rear pointer. So labeling goes like this. This is the front end. We will be taking out values from this end. This is the rear end. We will be inserting values at this end. There are 4 values, and the size of this queue is 4 in number. We have no other spaces left in this, so we can say that the queue is full. The index of this queue, this is an array, so the index goes like this: 0, 1, 2 and 3. The size of the array is 4. The indices are 0 to 3. If Q is the name of the structure, then Q of 0 represent 55, Q of 1 represent 67, Q of 2 is 30, and Q of 3, the last element, is 80. Naturally, the first element to be added into this list is 55. So it goes to the front of the queue. Then comes 67, 30 after that, and 80 at last. So insertion will be done through this path only, and we will be taking 55 first, then 67, then 30, and at last 80. So whenever we fill this queue with 4 values, it is considered as queue full. There will be some changes in this definition, what I have told you just now. We will see that after some time. So these are the terminologies used along with the data structure queue. This is a queue full condition. So these are the basic operations performed in this data structure. Enqueuing, that is for storing an item to the queue or adding an item to the queue. Dequeuing, removal or deletion of an element from the queue or taking out an element from the queue. Peek, it is used for accessing the front element in the queue, but we will not be removing that from the list. Then is full is for checking whether the queue is full. Is empty is for checking the emptiness of the queue, and we will be using 2 pointers. They are front and rear. As with the stack, we have a structure for queue also. The structure tag is used as queue here, and it's not compulsory to use this word. We can use any word here. It is user dependent, and we will be using an array because it's a group of elements, similar elements, and it has to be defined with a size. I'm using it as max. So item is the name of the queue, and it can hold this number of values in it, and we'll be using 2 pointers front and rear. It is similar to that of a stack. In stack we were using an array name with a maximum value, then int top for operating point. So since we are having 2 operation points here, we are using it as front and rear. Both of them are integer values. Let us see some states of queue. This corresponds to the labeled diagram we have seen before. This is the deleting end, and we will be having the front pointer. This is the insertion end. We will be having rear pointer. These front and rear can move. Front can move towards its right, so as rear it can also move towards the right. Why it is moving like that, we will be knowing in a short time from now. So this is the structure of a queue, and we can insert values in these cells. These are identified by the queue name or array name along with the indices, which starts from 0, 1, 2 and ends with the limit, upper bound limit max minus 1 if the beginning limit is or starting limit is bound is 0. If it is 1, this will be max. Since it usually we used to start with 0, so the maximum limit is max minus 1 if the size declared is max. So this is the indexed marked structure of a queue. As the initial case, we will be initializing the pointers front and rear with the value minus 1. We know that any value outside these ranges, that is minus 1, minus 2, minus 3, etc. towards this side, and max, max plus 1, max plus 2, etc. towards this side, are considered to be invalid indices. So the closest invalid indices on both the side of this valid indices are minus 1 towards this end, max towards this end. So we'll be initializing the values of pointers as minus 1, an invalid index, as we have done with top in the case of stack. So these are initial values. If initial values are minus 1, then we will call that state of the queue as empty queue. So whenever we don't have any element inside a queue, the pointers will be having the values minus 1. Keep that in mind. Now we are adding an element through the rear. So it has to be kept in item of 0. So 9 is being added. So item of 0 gets 9. When there is only one element in the queue, the front value is 9, so as the rear value. So inside this queue, who is at the front? 9 is at the front. Who is at the back? 9 is again at the back. So when we insert the first element, there will be only one element in the queue, and both the front and rear pointers point to the same location. Understand? So if you remove an item from here, then front will be moved to this place. If we add an element to this list, rear will be moving to this place. So when we go on adding elements one after the other, rear will be moving one step next to the previous one. So addition causes the movement of the pointer rear. Deletion causes the movement of the pointer front. I'll repeat. Addition causes the movement of rear pointer, and deletion causes the movement of front pointer. Both these pointers move to the right side. Okay. So we have added two more elements, 5, then 3. So there is no change in the front pointer because we have not done the removal operation. We can change the front pointer only with removing operation, and we can change the value of rear with addition operation. We have added two more values here. So rear has moved from 0 when we added 9, then rear moved to 1 when we added 5, it moved to 2 when we added 3. So the values of front and rear will be the index values, current position of the index values. So element having 3 values at front will be having the pointers as front equal to 0 and rear equal to 2, so that the indices of the elements are 0, 1 and 2. Now we have done a deleting operation. I have told you that with the delete operation we can move the front pointer. So the front value is gone now. Now who is at the front? 5 is at the front. We will not be moving 5 to this place. Instead, we will be moving this pointer. Front pointer is moved from 0 to 1. So we were having 3 values here. After removal of an item, we will be having only 2 values. 3 minus 1 will be 2. So the front will be pointing to 1. Rear is now at 2. So the indices are 1 and 2. 0 is gone now. So front is 1 and rear is 2. Again we are making one more removal operation. So again front is being changed from 1 to 2. Rear remains the same. Why? Because we have not added any item. I have told you that with addition only we can move the pointer rear. With deletion only we can move the pointer front. We have done 3 additions first, then 2 deletions, and now front is pointing to 2, so as rear. Rear is also pointing to 2. Such condition, that is when front and rear point to the same location, gives us a state that the list will be having only one element. In the first case also this happened. When both front and 0 were pointing to the same location, it was having only one element when front is 0 and rear is 0. This state can appear or happen anywhere in this list. If front and rear point to this location, say 4, then there will be only one element in the list. Because we have not added anything to these slots, we have removed everything added to this area, that is for 0, 1, 2 and 3. Then we will be having only one element at location 4. At that time front will be equal to 4 and rear will also be equal to 4. So the values of front and rear will be the corresponding index at that situation. So when front and rear are of equal value, we can confirm that the list is having only one element.